In the previous video, we talked about intensity and how the intensity that your ears can detect can vary from 10 to the minus 12 watts per square meter up to 1 watt per square meter. That's a range of 10 to the 12. Now it's more convenient to define a different scale for describing the intensity level of sound. And this scale is the Decibel scale. It's a logarithmic scale, and it's more useful because, first of all, the numbers that you get are smaller, easier to deal with. You're not dealing with huge powers of 10. And also it just matches the feature that human hearing is logarithmic, not linear. So let me show you how this intensity level, or decibel level, is defined. The decibel level, beta, Greek letter beta, is defined as 10 times the log of the intensity of your sound divided by that minimum intensity, the threshold of human hearing. So remember, this threshold of human hearing is 10 to the minus 12 watts per square meter. I usually like to say decibel level instead of intensity level. Intensity level is kind of a bad term because intensity level is this definition, and intensity is this thing, I. So it can be confusing when people say intensity and intensity level because they mean two completely different things. So I usually prefer to say decibel level. That's less ambiguous, and it's more common in audio for people to talk about decibels anyway. So let's see some examples of decibel levels and how this calculation works. So for example, when the intensity of sound equals that threshold of human hearing, if you're playing the quietest possible sound that human ears can hear, then beta equals 10 times the log of I naught over I naught, or 10 log of 1. And if you remember how logarithms work, the logarithm of a number is the power that you have to raise 10 to in order to get that number. If you raise 10 to the 0 power, you get 1. So the log of 1 is 0. So when you do this calculation and you get a number, you write decibels, dB, next to it. So 0 dB is the quietest sound that humans can hear. That's why we wrote this definition this way. Let's say we have an intensity that's 10 times louder. Let's say I equals 10 to the minus 11 watts per square meter. All right, our decibel level will be 10 log 10 to the minus 11 watts per square meter over 10 to the minus 12 watts per square meter equals 10 log 10. The log of 10 is 1 because you raise 10 to the 1 power to get 10. 10 times 1 equals 10. Let's do one more. Let's say I is, again, 10 times bigger. 10 to the minus 10 watts per square meter. Then beta will be 10 log 10 to the minus 10 over 10 to the minus 12. Units cancel. It's 10 log 100. The log of 100 is 2, because 10 to the 2 equals 100. So 2 times 10 equals 20. And this is a general rule for decibels. When the intensity increases by a factor of 10, the decibel level increases by 10. All right, now I want to do an example from the textbook. Before I do that, let me write down a few decibel levels for some common situations. 50 decibels. That's the decibel level of a normal conversation, when people are talking at regular conversational volume. "60 decibels is probably how loud I'm talking right now. I'm talking louder than normal conversational volume because I have my professor voice happening right now. Now 120 decibels is the number you get for that threshold of pain. Remember I said when the intensity is 1 watt per square meter, that's when you start to do damage to your ears. So if you put 1 in the numerator here, 1 over 10 to the minus 12 is 10 to the positive 12. Log of 10 to the 12 is 12. 10 times 12 is 120 decibels. So this is hearing damage starts. And that might happen at a loud concert. "130 decibels could be some heavy machinery like a jackhammer or a gun. "150 decibels would be if you're standing next to a jet engine. So if you're in any of these situations, you need to wear hearing protection, otherwise your hearing is going to be damaged, maybe permanently. In fact, I think OSHA guidelines say that if you're in a work environment that's 85 decibels or louder consistently, then you need to wear hearing protection. Okay, I want to do an example problem. Example 14.2. So let's say you're in a work environment where there's a noisy machine that produces a sound intensity of 1 times 10 to the minus 5 watts per square meter. So let's figure out first the decibel level of the machine. We'll use our definition of decibel level, 10 log intensity divided by that minimum intensity, the threshold of human hearing, oops, that's 10 to the minus 5. So 10 to the minus 5 over 10 to the minus 12 is 10 to the 7. The log of 10 to the 7 is 7. 7 times 10 is 70. All right, now let's say you add a second machine. Maybe turn on a second machine in that work environment. What's the new decibel level now? So the new decibel level, we have 2 machines, so the intensity is twice as big. 2 times 10 to the minus 5. Oops. Now check this out. This is 10 log 2 times 10 to the 7. And what you can do with logarithms like this is that logarithms add. So it's 10 times the log of 2 plus the log of 10 to the 7. And a handy rule of thumb, a handy fact to keep in mind, is that the log of 2 is about 0.3. The log of 10 to the 7 is 7. So this equals 73 decibels. And we've just discovered a rule about decibels, which is that when the intensity doubles, the decibel level increases by 3 dB. Anytime you double the intensity of sound, your decibel level increases by 3 dB. All right, I think I'll leave part C for you to work on your own.